gone. They just want to document it. Okay. So if you think about the life cycle of research, you have to wonder what are the earlier phases, right? Obviously, the research while it was happening is which is before the publication came out, and that's something you are familiar with, right? You're engaging in research. But then you have to ask what happens before that. And many of you know that your professors go and write grant proposals, right? How many of you have participated in writing grant proposals? Either to science department of, okay. All right. Do students get involved? Do they help writing proposals, or they? Oh, you did? Okay, good. And I hope you will involve more GNU students in that process. And it's really a good learning to see, what is the earlier part, okay? Now, usually when we write proposals, it's in response to a request for proposal. So you may wonder, where do requests of proposals come from, okay? So this is actually showing you the process, this nexus on, what happens even before the request for proposal comes out. There is a brainstorming and strategizing. And this one, we were lucky to get involved even in the earlier phases. So this would be a very different kind of thing, but it may be an interesting exposure to the earlier parts of the research life cycle. Okay. All right. So for evacuation route planning, as I said, before we get into the technical detail, we'll spend about 5 minutes watching this video. Some of you saw that a year and a half ago when I visited JNU, but for many of you, it's probably been new.
On the music that's criticizing the president.
And what would happen if a disaster struck the Twin Cities? On September 11th inspired a Minnesota man to try and help save lives.
Okay, well, the heat's on for FEMA this year. It's hard to believe, but hurricane season starts in less than a month. The most memorable images from last year's disastrous season are the failed evacuations and people unable to get to safety.
Are we going to see a repeat in years to come? Well, maybe not, thanks to a new tool that's being developed at the U of M. Here's Trish Van Pilsen. Those predictions sent more than 2 million people in Texas headed north. I figured they're not moving. Even here in Minnesota, we watched, horrified and helpless.
We all saw in the hurricane situations a bunch of taillights that are just gridlocked on the highways.
60 people dead along these roads trying to escape the wrath of Rita.
And then all of a sudden it blew up.
But no one watched more closely than a U of M computer science professor named Shashi Shekhar.
The incidents, after Katrina and Rita really shows that, even though our first responders try very hard, I think they are handicapped by the lack of scientific knowledge and the lack of good tools.
Both of which Shekhar believes he has. In fact, a computer program he and his team are in the process of developing might have dramatically cut the time it took planners to unsnarl the Texas evacuation.
On the roads, freeways became parking lots.
In Texas, the plans essentially said that they don't need contraflow.
Contraflow, meaning changing highway traffic flow so that all lanes lead away from the storm, which eventually they did in Texas, but only after the governor stepped in.
And it took them 6 hours to identify which routes, call the people, implement it.
Shekhar's program uses math to figure the best way out of a disaster area, whether that means an entire state, a city, or just a neighborhood. It was 9/11 that first got Shekhar thinking about evacuation and tinkering with the technology. Imagine trying to figure out the logistics of an evacuation of the entire Twin Cities. There are 1 million people and 60,000 vehicles in the 10-mile area surrounding the Twin Cities. Shekhar's program calculates that it would take just a little more than 9 hours and 1 million different routes to get everyone out of the 694, 494 ring. It's an extreme example, but the software has already been put to a more practical test. When Minnesota's Department of Transportation needed someone to craft an evacuation plan for the Twin Cities, they called on Shekhar. Based on his calculations, state planners radically changed their evacuation approach, deciding that people should walk rather than drive. In In some areas, people would walk about a mile, then be picked up by mass transit and evacuated to safe zones. The state has already run computer model evacuations of 5 different places in the Twin Cities. Fox 9 asked Shekhar to show us what it would look like to evacuate the Great Minnesota Get-Together. Suppose during the height of the state fair, there was a major chemical leak and everyone had to get out. If fairgoers jumped in their cars and drove, it would take 9 hours to clear 100,000 people out of harm's way. It would take 2/3 less time, or just 2 hours, if everyone walked a mile and were then taken to safe zones by city buses.
It increases the safety for the people of Minnesota.
Minnesota's safety folks love Shekhar's computer program.
Well, it's a lot quicker than trying to hand map it out. It's also much faster than the other commercially available software that takes hours or days to run. This one runs within a matter of seconds or moments.
And the program may spread beyond the state's borders.
Sounds to me like if it isn't, not only does it have an application here in Minnesota, but it has a nationwide application across our country. And if we can help others with technology that we develop here, we certainly ought to be willing to do that.
Seem kind of complicated? Well, staff at the U of M are working to try to make the program very user-friendly so any first responder around the country can navigate the program with ease. I'm Trish Van Pilsum for Fox 9 News.
Okay, so first question is, in this whole project, where was computer science? Why was a computer scientist involved in this project? Routing algorithm. But you kind of heard the response time. The traditional algorithms take a while. So that's one way computer science comes in the play. Okay, so that's the technical detail we are going to next. Okay?
Plus planning of network analysis.
Yes, this one has a lot of network analysis. This is all flow networks, so you will see dynamic flow networks. Okay, so we'll get started. Hopefully others will come and join. So I'm going to skip the earlier part, but notice that from computer science perspective, we talk about this as spatiotemporal flow networks, because that's the formal model. And this was another lesson. All this had happened, even the Fox TV video had come out, and I called the National Science Foundation program manager in computer science, and I was telling her all this has happened, and we'd like to get some research grant from National Science Foundation. And that's the question she asked: where is computer science in everything she said? So that was really a major message to us when we wrote the proposal. We just completely changed the language. So all this evacuation and so on is the one page in motivation, and rest of the proposal said spatial graph, spatiotemporal graph, flow networks. So you will see that translation. So again, acknowledge this work had many individuals. Besides University of Minnesota, the local Department of Transportation and consulting firm, and you are going to see a whole lot of other people, police, National Guard, and so on. Okay, so I'm going to skip actually presentation of what my overall research area is, but you probably saw spatiotemporal data mining, spatial data mining. We spent a whole day on that. And then we have been in the routing game for a very long time. Believe it or not, what you see in Google Maps, where the research project in 91, 92. Okay? And this one, evacuation is the one we will talk about today. So without further ado, let's quickly talk, go there. And so we'll talk about the motivation, which is probably pretty obvious to everyone. Fox TV talked about it quite a bit, so we'll just browse through it. Try to define the problem from a computer science perspective. Talk about the hardness, where is the real challenge, related work, and then this is where the technical details are. Okay. So by the way, if you were in Florida and hurricane-oriented places in US, the evacuation routes are marked because they have to do it so often that they actually have designated and marked. Okay. If you look at overall transportation community certainly gets interested in it. These are the national research priorities from transportation community, and one of which includes emergency preparedness. And just a aside for some of the, so Professor Min, you also see equity is another thing which shows up in these things. So outside computer science, a lot of social issues start to show up. Okay, and particularly Hurricane Katrina and Rita, the one you saw in Fox TV, that really woke up the transportation community because that's where the problem ended up being. Okay. So we heard this story, Hurricane Rita, certainly this evacuation lasted many days and there was like 100-mile long traffic jam. And even 10, 12 years before Hurricane Andrews, you had same problem in Florida, where many people chose to go back home rather than evacuate. They couldn't really tolerate sitting on traffic that long. So, but in general, for Department of Homeland Security scenarios, there are many other cases for which you need evacuation. So they have made a list of about 14 types of threats. Half of them they require evacuation, other half is shelter in place. So here I am showing you one other graphic which was made by ESRI. And the scenario here is Houston Galveston, which is a big oil refining area. And the scenario is that one of the oil refinery has an accident and you have all these gases coming out. So in this kind of scenario, the very first thing they do is a plume simulation. Okay, this is where you need aerospace and chemical engineers and others. So with the plume simulation with differential equation of heat and mass transfer, you can kind of say, well, given the wind, if I know the weather, given the wind, the chemical is likely to go that way. Okay? And then you kind of get the footprint. So this is the area that from where people may be kind of under threat. And depending on the chemical, it's either shelter in place or it's evacuation. So in this case, we are saying evacuation, in which case you need to bring in transportation network, try to figure out the path. You also need to kind of look at many other aspects of the map, such as population and so on. So, so as in US after 9/11, there has been a lot of emergency preparedness aspect, and they have made a list of a whole bunch of scenarios that every community needs to be prepared for. Okay. There is another place where there is a legal requirement to have evacuation plans, and this happened because of 3 Mile Island accident in 70s. How many of us actually know this name or know what 3 Mile Island was? So this is in near Pittsburgh. The nuclear power plant was on this island, and they had an accident, sort of like Chernobyl, not as bad, but several years before Chernobyl. And again, in nuclear power plant, as you know, the radioactive material kind of comes in the air, and it would have a plume. And certainly there is major health hazard. You don't want to leave people there for very long. So after 3 Mile Island, there was a regulation made in US which every nuclear power plant had to have an evacuation plan on file for 10-mile radius. Okay? And that's remained as the regulation till recently, but except after Fukushima. Okay? How many of us remember that accident? Quite a few. And how big was the plume for Fukushima? Some say it went about 50 miles. Okay, they have a much bigger plant. So there have been a lot of debate, and these regulations may be revised. Okay, but at least these are regulated. And in Minnesota, there are 2 nuclear power plants just around the Twin Cities, and the community has to be prepared for that, legally required. Okay. Oh, it's not. Okay, maybe make it 1. So right now it's on 0. Should we make it 1?
No, it's not switched. The on switch is not on.
Okay. Power strip. So usually in computer science or databases, we also talk about fault tolerance. If you were in database, but most of the faults we are worried about is usually power failure. So it's an interesting thing. But more and more people are concerned about natural failures. So the data centers and all, they have to be prepared to face earthquake and tsunami. And they talk about triple continental redundancy. Your data centers have to be quite far apart. And actually under this threat, in US, mostly the dirty bomb attack scenarios, they think is about less than 50 mile. So all the critical even data centers have to have a backup data center 50 mile away. So some of this comes directly to computer science, but we'll look at this more. All right. So hopefully motivation is clear. We know why we are talking about this evacuation. Okay, good. All right. So let's try to formulate the problem, which looks familiar to computer science world. And computer science, at the least, we want to talk about input and output. And if we want to do a optimization kind of framework, then we want to add objectives as well as constraints. So in this case, we thought at least these three data sets are needed. One is your transportation network, which we have seen before, but the only new aspect here is we want to know capacity of each edge, okay? Because in evacuation, just you heard, the transportation network capacities are overwhelmed, right? The number of people leaving often is far more than what your roads can carry, okay? So if you don't model the capacity, you are going to again run into what happened in Houston. So these are really not simple graphs. If I add capacity constraints to the edges, what is the name we use in computer science for graphs where capacity constraints are modeled? Flow networks, okay? So flow network algorithms, many of you will study. Certainly Corman's book would have chapters and many of you will do a lot more, okay? All right, so that's the transportation part. Then we need to know, how many people are leaving, where they are, okay? And the last part is the destination. In case of the nuclear scenario, usually most of these folks have to go to a treatment center, okay? They have to be given a medicine which will reduce the effect of radiation. All the cars and vehicles, they have to be washed, otherwise they remain radioactive and so on. So in case of nuclear scenario, they all go to a certain place or a set of places and get treatment. But in other cases, they may just have to leave the affected area, just leave the radius and so on. Okay. All right, so what is the output? So certainly we need a set of routes, okay, through which people will travel. But it turns out that, all these routes don't usually have enough capacity. So you have to use the same route again and again. So you may also ask for a schedule. Okay, when should each person leave? And these are called phased evacuations. So usually in case of hurricane and so on in Florida, the 2 or 3 days before, there will be just a general spatial request. Hurricane is coming, this area is likely to be affected, try to get out. But as the time gets closer to the landfall, the last 24 hours, it becomes a phased evacuation. And you say, okay, this area leave first. Okay, right now, the next area leave an hour later, next area leave an hour later, because trying to control the capacity issue. Okay. All right, so this is your basic input output. In terms of objective, as you said, from the domain perspective, we want to minimize the evacuation time, right? How quickly people can get out. And then there are a lot of different constraints. The biggest one is the capacity. Then you may have other constraints related to computer science aspect and so on. Okay. So here from computer science perspective, this is an interesting question, right? Domain is largely interested in this, but obviously if that's all I'm doing, it may not be publishable in computer science, right? So you have to also say, can I bring in computer science so that it's a win-win and you can play? So we have to explain this scalability or computational complexity back to the domain, okay? So what do you think is the value if I have a fast algorithm? Right? You heard a little bit of that in Fox TV, right? But why should domain people care whether my algorithm is very fast or very slow? Real-time response, which means if something changes in your scenario, right? Let's say evacuation started and then you had a big accident, a truck blocked a route. Okay, that route is now gone. So you may have to readjust your evacuation plan because of that. And if you want to do that, then you better have fast algorithm. You can't have an algorithm running for 3 days, right? So that's basically during the response. Okay, if something else happened, and it actually does happen. In case of Katrina, actually a major bridge was really flooded. Okay? In case of Rita, after the first day, life was so bad, then the governor had to step in and say, you have to change. Okay, whatever your expert told you is off the table. Okay, just do control flow. We need to improve situation, right? This happened during the event itself, and many events are multi-day events. In case of hurricane, it's at least 2-3 days long event, and I heard some other events are even longer. So actually, we just heard Kashmir floods. How long was that event?
We were there for 68 days.
68 days. Okay, so a lot of things change during that time, and you have to adjust and so on. In fact, most emergency operations center, they still prefer technologies where power going out doesn't affect them as much. So usually there is a big whiteboard which is two-sided. Okay, on the first side, you look at the current plan which has been pre-planned, and they keep executing that. But on the back side, they keep updating, saying, okay, new news is coming, this route is gone, or something else happened. And in the back side, they are now planning for the next phase. Okay, and after maybe a couple of hours, the board is flipped. Okay, now you switch to the new plan, and so on, and that keeps on going. So during evacuation itself, it's important to compute things reasonably fast. And also remember that after your algorithm is run and solutions are produced, they will not be used as they are. Okay, the people in the room would add a lot of domain knowledge and they will adjust it, right? So you have to leave time for the humans to tweak it. Okay. Of course, this is not as common of the activity. More common is planning. Okay, so all the communities have to think of various scenarios and they have to make a plan. And the value of fast computation in this case is that you can allow them to explore many scenarios. Okay, if your algorithm takes a whole day to run, they can only try a few scenarios, right? But if it runs in a minute or a second, they can run many more scenarios. So anyway, you have to explain the value of computer science to the domain before you can carry on. And then we'll continue. Okay, so just to give you an example of input output, just so that we understand the problem. So this is the example of the nuclear power plant. In this case, Monticello nuclear power plant, this is sort of your 10-mile radius. And in this, roughly the population estimate was 42,000 at the time they did this plant. Now it's a little bit more. And these are the hand-drawn evacuation routes. This is how the state of art is. Folks, they sit around a table and you bring a transportation expert, you bring other folks, and based on their knowledge and experience, they may look at a few maps in addition to that, but based on the experience, they hand draw these routes. Okay. So in this case, this is Monticello nuclear power plant. That's roughly the 10-mile radius. They want in this old plant to bring everybody to this high school, and this is where medical treatment and so on was planned. Okay. Since then, they have changed this plan, so don't take it too seriously. But when we started in 2002, this was one of the test case that was given to us and saying, okay, show us what is the value of your algorithm. Can you at least beat the hand-drawn plan? Okay. All right, so a lot of us have already studied networks, so let's try to see what are the weaknesses of this handcrafted plan. So when you look at this, do you see any problems or any places you can improve it? Okay, so basically they are taking two freeways, this 94 and Highway 10 is also US Highway 10. So these two are two major roads, and in here they are also using a lot of side roads. So any issues you see here?
So the 168, 169 and 10,
Mhm.
there are two highways converging at that node of Elk River.
Okay,
No congestion there.
wonderful. So you right away see the choke point, right? You right away see the choke point. So this choke point starts certainly on this road, and it's actually even bigger. If you think about a cut here, I have only two major roads going in, and over here I have so many more. So you are seeing a choke point, and you are going to see backups, right? And if you did a better algorithm in flow network, which is a capacity aware, it's going to figure out some way to address that, right? And that's one intuition. So when we ran our algorithm, we'll show you the solution at the end. It will improve things, right? So there is hope for computer science to add value. Okay, let's give you a second example, and this is indoor example. And this is sort of the AutoCAD drawing. How many of us have not seen a drawing of this kind? Okay, good. All of us have seen. Probably most building you will have an evacuation sign with this kind of drawing. So there are two floors. Okay, this is the ground floor with one meeting room. This is the the first floor, that's how we'll call it in India, with two meeting rooms up here, corridors, staircases, and these are the doors, right? So this is maybe a building where some people are meeting, and for some reason you may have a fire alarm going off or some other incident, and you need to evacuate it. Okay, so first you have to convert this building to some kind of a graph if we want to run flow network algorithm. And as I told you, this is where the bottleneck today is for indoor applications. There is no consensus what the nodes are, what the edges are. So I will just give you one way we did it. So in our case, we things like rooms and corridors which can hold people were thought of as nodes. Okay, and the doors and staircases where people have to move through were thought of as edges. This is one graph model. Okay, that's not necessarily the best graph model or the only graph model. You can come up with better ones. For example, this corridor, you may choose it to break into multiple nodes and multiple edges and so on. For large buildings and so on, you will have to do better than this. Okay, but just for a toy example, this will serve. So once we did that, now these blue things will become nodes and the other ones become edges. Now with nodes, we also attach some attributes. Okay, how many people maximum capacity this room has and what's the current occupancy. And same way for edges, we added not only travel time but also capacity. How many people can take this edge at the same time? How wide are the staircase and doors? Okay. All right. So this is the graph model, or more accurately flow network model. Can you recognize the meeting rooms here? Which nodes are meeting rooms? N3? Okay. Alright, so the way to think about it is here. Okay, so node have two attributes, maximum capacity and initial occupancy. And initial occupancy will give you a hint where people actually are. Okay, so these were the two meeting rooms on the the top floor. Remember these two. Okay, and bottom floor there was one. So that's the bottom floor. Okay, this is the corridor. Okay, the corridor, and then this is sort of the staircase coming down and so on. All right. So you can make correspondence, but once we have converted it to graph, we are in computer science world, and we can start playing with it. So this is the input. Okay, what does the output look like here? Okay, this is the input. So in case of output, I need to give routes to people at N1, N2, and N8, and say how are you going to reach the exits. Okay, so these routes could be specified in different way. Here is a tabular view, and I will also give you a graphical view. So first, people who were at N8, okay, remember N8, which is ground floor meeting room. We are basically saying, okay, you have 15 people, make a group of, 3 groups, 6, 6, 6. The first group could go down in one way, okay, and the second group will follow them. See, the both routes are same, just that their departure times and exit times are different. And then the last group will go the other way, okay. So just thinking about it, some people will go this way, and some will go that way. Okay, so two groups are going this way and one group is going that way. Okay, multiple routes, and then you are also pipelining it, the same route is used again, and so on for this. So it's much easier to visualize it in terms of a graphic. So let me quickly show you that. So basically these groups of people, first they are divided into smaller groups so they can travel together through the staircase and so on. And remember, staircase capacity is smaller than 10. Okay, so right here you can see this capacity is only 3, so you can only send a group of 3 this way at together. Whereas on the other side, again you can send another group and so on. So you first break this into groups of sizes which can travel together. Okay, so these are the groups D, E, F, I, H, G, and so on. And then we are giving the whole schedule. So T0 they are here. Then we say, okay, these groups can move, and I'm obeying the capacity constraints. Okay. Okay, 16 time units, in the ideal situation. This assumes, this is sort of the optimal solution. Okay, later on we'll come back and ask whether you can actually get it done in practice or not. But for now, let's stay in computer science and say, okay, we got you optimal solution. What the domain folks do with it, it's their issue, but we at least recommended a solution. Okay. So does everyone see the input-output pair? Do we understand what problem we are solving from computer science perspective? Okay. All right, so let's try to think about, is this problem hard? So when you look at this problem, okay, how many of us have taken flow network topic, either within Corman's book, read the chapter, or taken a course? At least one, okay. So in flow networks, what problem is, you would think is somewhat similar to the problem at hand? Right. Right. So what will be the name of problem that Corman will use, or a OR book will? Max flow min cut. Okay, that's a very well-known problem. It's used a lot for transportation and so on, and that's the closest thing. But there is one small difference. Okay, max flow min cut, your flows are sort of infinite in some sense, right? They keep on going. But here we have finite number of people, and after a while it finishes, right? But it's a good insight to always remember. So it's from computer science perspective, the capacity constraint is the choke point, and I'll come back to that. Okay, but from domain perspective, there are many other challenges. One of which is what data set is available. So I said, well, my input is I want to know how many evacuees are there, where they are. Do I really know that? How am I going to estimate that? Are there data sets available? Okay, today this problem is easier. 2002 it was harder. So today if I want to know where evacuees are, your solution will be, who knows about where people are today? Census thinks you guys are home, right? Who knows that you are over here in JNU? Your cell phone companies, right? So many people carry cell phone. Today you will go to the cell phone companies and say, I need this data, okay? But previously you had to go to other data sets and so on. There are other issues here. In flow networks in computer science, we think link capacity is constant. When you talk to transportation people, they tell you, well, not really. It depends on the load on the link. Then there are social science issues, which basically says, people, even if you are right here at JNU, if you were asked to evacuate, how many of you will actually straight away leave Delhi? And how many would rather go home and collect your family and others before you leave? Right? Most of you will go other way. So those are the social, issues, household modeling, and we don't actually have enough data and so on to do that. There are, policy issues. Even if we give out these plans, are people going to trust that? Are they going to comply? Okay, these are all kinds of issues. And and there is even scientific issues that whatever my algorithm produces, how am I going to actually validate? Is it really true? Okay, so there are all kinds of challenges. But obviously, as a computer scientist, we are going to focus on the computer science challenge, right? If you had an interdisciplinary team, you will go and address more of this. So let's think about computer science challenge. And as we heard that min-cut max flow is a nice relationship to this problem, and that applies if I look at this ratio, if the size of evacuee population divided by bottleneck capacity of transportation network. So this is what you get from that min-cut max flow. Min-cut max flow can give you bottleneck capacity. And once you know that, you can try to see how much is the overload factor. Okay. If there is no overload, which means your population is less than bottleneck capacity, okay, is this problem hard? No, you just say go to Google Maps and they will tell you. Okay, forget it. It's not hard. You can do your anything Dijkstra, A star, hierarchical algorithm. Now, if this ratio tends to infinity, then the problem is more expensive, but we know how to solve it, and that's the min-cut max flow you just heard. This has been studied a lot. Okay, so it's really interesting only if this is neither less than 1 nor very large. Okay, if it is 10 or 100 or something, that's where you have opportunity to do new work. Okay, so that's one thing to think. The other aspect that also follows here there are some issues in here which will actually confound A star and Dijkstra, and I will show that as we go along. Okay. For example, you saw that many people had to wait, and in A star and Dijkstra, the assumption is there is no wait anywhere. Okay, so you have to adjust these kind of old algorithms if you want to work with this. Okay? So computationally also it's an interesting problem. That's all. So it's worth for computer scientists to get in there. Any quick questions on what's the crux of the problem? Okay, basically capacity constraint is right. You have a lot more people than the capacity. All right. So let's now think about what solutions are already around, because evacuation is not a new problem. People have had to deal with it for many years. Hurricanes, it's not a new phenomenon, right? We have had that for many times. Fire evacuation, people have to do that. So clearly there were other domains who were studying this problem, and there are at least 2 other domains which have studied this. So initially, as a computer scientist, when we were going up to transportation officials to say, we think it's a cool problem, we would like to work on it, they will keep telling us, go figure out what has been done. In civil engineers, we did this, right? So I'll first tell you what we had to first understand. So in computer science, when you look at A star Dijkstras, they did not look at capacity, but min-cut max flow looked at it, but with infinite flow. So we can certainly look at some of those, but it only takes you so far. It's not addressing the crux of the problem. So the next community which had worked on it is operations research, and some of you heard about time expanded graph. That they started working on that in 1960. Okay, so long tradition. But the reason they had brought it up to actually formulate linear programming. Okay, so after doing all that, they basically formulate a integer programming, linear programming, or quadratic programming. And there were work done. So for example, in University of Florida, one of the professor, he visited NIST, which is very interested in building evacuation for fire. And over there, he created a model for building using time expanded graph and linear programming. And for a modest site building, the solutions you can produce in reasonable time. He even put out a public domain software called EvacNet. So this was around, and we first tested that. And actually, for a small scenario, if you just want to evacuate JNU campus, this is probably okay. You can run that in a minute or two, and it will give you the solution. But certainly, if you wanted to run it for the Houston size problem, okay, it will just crawl to a halt, okay, and we'll have to think about why, okay. So here are the run times. Small graphs, no problem, okay. Big graph starts to crawl. Okay, now you are in real trouble. And how big were the graphs we were talking about? You know, Delhi transportation network. How many nodes and edges are we thinking about?
Can't count.
How many?
Can't count. Sir.
Can't count. Okay. So Minneapolis, which is a much smaller city, it's about 250,000 nodes and edges. Okay, it's about 3 million people there. Delhi, I think, is about 10 million, right? Yeah. Maybe more. Yeah. Los Angeles, certainly in few millions. Okay. So you are way off down here. And that was just the static network. And remember, we are talking about time expanded graph. And how long was this evacuation going? Hours or days. So then you take the million node graph and you have to replicate it thousands and thousands of times. Okay. So you can ask your operations research colleague, if I give you a problem which has 1 billion variables, how long will it take you to solve it? And they will throw up their hands. Basically, after 100,000 variables, they cannot get exact solutions. Okay, there is some new effort now to get approximate solution where you can go up a little bit further, but certainly as you scale up, you know, which is what computer scientists love, right? So we are not out of business yet. So there's still hope. Okay, the next one they would keep telling, because transportation departments are dominated by civil engineers, and they have been actually doing something for commuter planning. So when they decide where to build the roads, okay, where to add a lane, where to expand capacity, they have their own model to mimic the commuter behavior, and those are called this dynamic traffic assignment models. And this is based on a game theory and Wardrop equilibrium using